Hey guys, so I'm going to do a second video on thermochemical equations. So thermochemical equations are just equations that you will see heat energy involved. So we've done all kinds of equations. We've balanced equations and we've talked about mole ratios with the coefficients. So a thermochemical equation is just putting in that energy that you see that we have seen so far. And we talked about enthalpy in the last video. And that's just going to add it into that equation that can be used then for a ratio, so to speak. So let's go ahead and get started with that. So as you can see in this equation, it is the decomposition of water. So I have 2 moles of water and it's decomposing into 2 moles of hydrogen gas and 1 mole of oxygen gas. And off to the right here, you see my delta heat of reaction, and it is 572 kilojoules. So because the kilojoules, these are positive, that it's putting that much energy into how your decomposition is actually happening. It's putting that much energy into breaking up water. So there are 2 ways that you can kind of write your thermochemical equations. You can either include the heat of reaction just kind of as a separate side, and the positive or negative will tell you whether it's being input or whether it's being given off. Or you can actually write the heat of reaction in your equation. So if I wanted to, I could have said 572 kilojoules plus 2H2O, and that also would have told me that that heat was being put into the equation and it was decomposing into hydrogen and oxygen. I can flip the equation, and if I flip the equation, you can see the delta reaction now is going to change. Okay, so if I flip it, now hydrogen and oxygen are forming water. And when you flip that, you notice that your delta reaction is going to be negative now. So that's how much heat energy is given off. So when you flip the equation, you're going to also flip the sign, because up here you were breaking down water. Okay, and that's how much heat was being put into breaking it down. Down here, you're forming water, so that's how much heat energy is going to be given off. So your positives will always be on the reactant side. Your negatives will always be on the product side. So again, I can either write it off to the side just like this, and the fact that it's negative tells me that it is being given off, or I could write 2H2O plus 572 kilojoules. Okay, it's not going to be negative in the equation, but you'll know that it is a negative number because it is on that product side and it's being given off. Okay, so just like we've talked about in the past, any kind of mole ratio that we have done, we can compare moles to each other, but you can also look at now your energy involved, and you can create a ratio with that. So this specific equation gives off negative 572 kilojoules. So I could write an equation or a ratio really that looks like 2 moles of hydrogen takes this much kilojoules, 1 mole of oxygen takes that many kilojoules, 2 moles of water takes that many kilojoules. So you can write any part of your reaction as an equal to the amount of energy that's either being put into it or being taken out of it. So you're going to use your heat of reactions kind of as a ratio in order to convert, and I'll show you what that looks like. So on this page here, your size of your delta H, your heat energy, depends on the amount of substance you have reacting. So if you look here, I have, as I said before, 2 moles of H2O and 1 mole of O2, creating 2 moles of water, and that's negative 572 kilojoules. But let's just say that I multiplied all of this by half. So I could divide it by 2. It's the same thing. So if I divided all of these by 2, notice now instead of 2 moles of hydrogen, I only have 1. Instead of 1 mole of oxygen, I have a half of a mole of oxygen. And instead of 2 moles of water, I only have 1 mole of water. But my kilojoules, my delta H reaction, my heat of reaction, also gets cut in half. Again, that's the amount is going to really dictate, again, how you calculate all of this. So if I'm dividing all of these by half, I have to do the same thing to my energy, because the more you have, the higher your energy, the less you have, the lower the energy. So this just shows you, if you were to cut all this in half, you have to include your heated reaction in that as well. It takes a little bit less energy because you have less amount present there. So you can determine your heat of reactions by being endo or exothermic, just based off of whether your heat of reactions are negative or positive, okay? Or depending on where they're located in your equation. So if you look in this reaction, I have Al2O3 plus 1,676 kilojoules, and that gives me 2 moles of aluminum and then 3/2 of a mole of oxygen. And again, sometimes you'll see these fractions here with Thermochem. A lot of times it's just to simplify it, but when you're looking at the actual equation here, this number, because it is written on the reactant side, tells me that my equation is endothermic because my heat energy is on the reactant side. It's being put into the reaction. And so if I gave you this equation and said, okay, well, what's my delta H? You would write positive because it's on the reactant side. So it's a positive number, 1,676 kilojoules. Had this been on the reactant or the product side, then this would be a negative number and this would have been exothermic. So use your equation to kind of determine, is it endo or exothermic? That'll tell you whether you have a positive delta H or a negative delta H. So we're going to use equations to set up ratios, similar to what we did with stoichiometry and mole ratios. So if you look at this reaction, same one I just had, and if you look, it's asking for how many grams of aluminum can be formed when 1,000 kilojoules of heat is used. So again, you want to look at what the equation is giving you, what the problem is being, what it's the information it's giving you, and what it's asking you to actually find here. So in this case, it's giving me 1,000 kilojoules of heat, and it's saying, well, if I give you 1,000 kilojoules of heat, how many grams of aluminum can I form? So you're going to set this up with a T-chart, just like any other kind of mole ratio that we've done this year. And if you'll notice, I'm going to start with what I was given, which is 1,000 kilojoules. Okay, remember that whatever unit is here has to go down here. So you need to pay attention to the amount of kilojoules given to you it's either going to be in the equation or it's going to be given to you just as your delta H. So I have 1,676 kilojoules down here. And the ratio is, if I have that much, I'm going to get 2 moles of aluminum to form. So that's my ratio, 2 moles of aluminum over this much heat energy. And again, I put heat energy on the bottom because I'm starting in heat energy and I need those to cancel. This specific problem asked me about grams of aluminum. So I'm going to take the moles that I find and I'm going to convert that to grams just by multiplying by its molar mass. So again, molar mass you get from the periodic table. So when you have everything set up, you are converting yourself from heat energy to how many grams of aluminum I end up with. So if you multiply across the top and then divide by 1,676, you get 32.2 grams of aluminum. So again, per my equation, I know that this much heat energy would give me 2 moles of aluminum, but I only had 1,000. I had less than that. So I needed to use that as a ratio to try and figure out, well, if I have only 1,000, how many grams am I going to get? So that was just a heat energy to mole, and then once you're in moles to grams. So when you do this, you're going to set your heat energy equal to a mole ratio. So again, those numbers come from your balanced equation there. Okay, so let me show you another example here. Okay, for the reaction of mercury to oxide, decomposing into mercury and oxygen, my delta H this time is positive, 182 kilojoules, just like it was in that other equation, it was positive. So how many kilojoules are needed to react with 25 grams of mercury to oxide? So this one is pretty much flipped of what our other equation was. If I'm going to flip back here to the other slide. This, we started off in kilojoules and I ended up in grams because that's what the information the problem gave me. Whereas in this problem, it's starting me off in grams and it's asking me to find out, well, how much kilojoules is that? So now you're starting with 25 grams of mercury 2 oxide. So again, write down what you've been given, 25 grams of mercury 2 oxide. Okay, I'm in grams. I can't go very far in grams, so I know I have to convert that to moles. So I have to find the mass of HGO from the periodic table, which is 216.1 grams. I convert from grams to moles, and now that I'm in moles, I can use my equation for my mole ratio here. So in this problem, 182 kilojoules gives me 2 moles of mercury 2 oxide. So I'm going to use that equation. Moles is going to go on the bottom because, again, whatever unit is here, I need to cancel. So I'm going to put moles of HGO down on the bottom, and then that's equal to my delta H, 182 kilojoules. Multiply across the top, multiply across the bottom, and when you are done, you get 10.5 kilojoules. So I need 10.5 kilojoules to react with 25 grams of mercury 2 oxide. So if I was only given 25 grams, I would need about 10 and a half kilojoules in order to get that to decompose like you see it here. Okay, so you're just using your delta H, your heat energy here, and you're trying to figure out based on the equation that's given to you and based on the information it's asking you to find, you can convert with heat energy and moles. But as you've seen here, a lot of times you're not just given moles, oftentimes you're given grams. So you would start in grams, go to moles, go to heat energy, or you can go the other direction. You can start in heat energy, go to moles, and end up in grams. But the point is, if you are in heat energy, your only option is to go to moles. Okay, so you can't go right from your heat energy, your kilojoules, right to grams because this is a mole heat energy ratio. So make sure you would go heat energy to moles first, and then you could convert to grams if you needed to do that. Okay, there's a lot of different kinds of enthalpy change. And again, when we talked about enthalpy before, we talked about the heat of reaction, which is how much was actually used or either given off or being input into the equation. I could have the heat of combustion, which is essentially burning something. So I could figure out how much heat was given off when something was burned. The heat of neutralization is given off when you are mixing an acid and a base. We talked a little bit about heat of vaporization and heat of fusion when we did the heating and cooling curves. Remember that the heat of fusion is just the amount of energy needed to melt 1 mole of a substance versus the heat of vaporization, which is how much it takes to vaporize 1 mole of a substance. So all of these, there's a lot of different types of enthalpy change. And again, you're just using these as conversion factors per your equation. Okay.